Good afternoon. This is week 11 of Advanced Computer Architecture CS 470. We are starting today the third and last part of this course on hardware security. You'll soon see why hardware security in this course. There are a number of attacks that are are going to exploit all those beautiful microarchitectural features that we have been working on in the first part of the course. So it makes sense that we connect what we have done for a good purpose, performance, with what these features can be used for in a malicious way. So why are we discussing hardware security? There are a number of reasons to that. The first, connected to hardware and architecture, which is what we are covering in this course, is the fact that maybe we can get help from architecture to handle some insecurities that come essentially from software. OSs and hypervisors are in general what is in charge of the isolation between processes, between users, and therefore help guarantee a number of security properties that are seen as essential by users of computing systems. Except that these OSs and these hypervisors in particular have grown to be huge pieces of software, especially hypervisors, right? I hope everybody's familiar with what hypervisors are, but they are a sort of a super OS in some sense, right? This is the part of system software that creates these containers inside which the OSs run. And it uses essentially the same bag of techniques that the OS uses to separate different users. Hypervisors use the same bag of techniques to separate different OSs from different completely different users of the computing equipment. Hypervisors were meant to be extremely small pieces of software, and they are now huge pieces of software that are naturally likely to have their large bag of bags. So the problem is, can we trust OSs and hypervisors? And of course, the answer is probably not, right? If you look at the number of the statistics on number of bugs per page of code or whatever sort of statistical information about how many bugs there are, you must conclude that there are probably thousands and thousands of bugs in an hypervisor, and some of them are certainly going to create problems for security. So maybe the isolation should actually be enforced more at the hardware level than at the software level for increased security. The second reason is of involving hardware in security is that there are a broad class of attacks where the attackers discover our secrets because isolation is broken at the level of microarchitectural features. What I mean is that the way we have isolation typically in our systems is not by cryptography, for instance, not because another user, another process that is running on the same processor has encrypted the data so that I cannot see them, but just because there is an architectural separation between the two. The processor and the operating system is built in such a way that there is reasonably no way for me to see what is the content of the registers in a different process or in a different process that is running in simultaneous multi-threading with me. So there are two sets of registers in the architecture at the same time, but there is no reason, no way, whatsoever for the owner of one set of the registers to access the other set. And this is not necessarily broken. There is, I don't know of any attack that really breaks this directly, because the architecture, if there are no major bugs in the hardware architecture, there will be this separation. What is a problem is that there is also microarchitectural state. And you remember the distinction that we do between architecture and microarchitecture. Architecture is what the programmer knows. So we do know that there are registers of one virtual processor and the registers of the second virtual processor alive at the same time in the machine, and they are isolated. But then there is the microarchitectural state, that is the state that is not known by the software developer, and that corresponds to the state that I added to the machine to make it work. Think of the reorder buffer, think of the reservation station, think of things even much more trivial, if you want, the caches, right? Which are not an architectural state, because the cache doesn't exist for the programmer, right? For the programmer, you ask memory and you get, you do a load and you get the data, and that's it. All these microarchitectural state is naturally not protected in some sense, right? Because nobody should be accessing it. It's invisible to the programmer, but is there. And so there are a large number of attacks, a variety of attacks that go and use the fact that there is some microarchitectural state to gain access to the secrets. The last reason to speak of hardware in the same setting as security is that there is yet another broad class of attacks that depends intrinsically from the physical properties of the implementation of our computing systems. And these kind of attacks are extremely important or may gain more even importance in the future for a couple of typical settings. One is that as a user of a computing equipment, I may not have any more physical control on the computing equipment. If I'm a bank, I have my data center inside the bank, is physically located somehow on my premises, and I can guarantee that nobody can be touching my hardware literally, physically at any point in time. But if I'm using Amazon instead, I don't even know where physically the data center is, let alone having any idea if anyone is tampering with the hardware, right? I may trust Amazon, I may not trust Amazon, and then these kind of attacks become extremely dangerous, because by looking, by monitoring, by doing something on the hardware, they may learn my secrets. Another situation where this is extremely concerning maybe more in the future than in the present times is what people call IoT, Internet of Things. The idea that there will be a lot of components of the computing system that will be dispersed in the nature. And because they are somewhere else, clearly I do not have physical control on the device, and maybe this exposes particularly well to the device to tampering, to some physical monitoring. So what we are going to do in the next 3 lectures is address essentially a bit these 3 points in a slightly different different order. We'll start by doing in this lecture a sort of a review, a quick visit of a number of these side channel attacks that I call microarchitectural. It's not an official name, but I think the underlying component to all these side channel attacks is exactly to exploit the existence of microarchitectural state, of something more than the state of the processor or of the computing system that is known to the programmer, but the fact that there are internally some secrets. So this connects very, very strongly to what we have done in the first part of this course, CS470, right? Because we have been developing architectures with very peculiar internal state that was helping us to go fast. And you'll see that I want to say almost everything that we have done at that level will be sort of turned against us from the security perspective. The second lecture will look into this idea of trying to enforce isolation between processes, between users in a different way by using hardware to create this separation, just because of what we will see today is that intrinsically the way we build system, and we need to build them to be fast and effective and efficient, will make them almost impossible to protect. And so we'll try to go in a different way to try to protect and to create isolation than the classic way that we hoped to be safe. And the last lecture will be dedicated to this physical side channel attacks. This time, maybe the name is more official, is the side channel attacks that exploit physical emanations from the system, like electromagnetic waves or temperature or even noise has been used. They are not a huge concern today for traditional general purpose computing. I think that data centers have many other concerns in security these days that are much more pressing than physical side channel attacks, but they are extremely critical for embedded application. They have been since ever for some classes of users like smart cards, right, that contain processors, and they are always in the hands of the customers and therefore potentially in the hands of the attackers. They can be studied, analyzed, and it makes these attacks the perfect way to learn secrets. And as I said, also IoT is one of these areas. So we'll see this class of attacks in the third lecture. They are also extremely powerful. In a sense, I want to say much more than the attacks that we will see this week. They exploit statistical analysis and some math that make really out of what is that what appears as complete noise, they make data and secrets visible. So I think they are extremely elusive and it's not very clear in many cases how to correct them. So what are we going to do today? As I said, I think I said it already, is going through a set of classic attacks. We'll go through a couple of definitions initially, but then we look at attacks that maybe are not side channel attacks, these raw hammer attacks that are still a physical attack possible from an architectural level. And then we look at these architectural side channel attacks, a few of them with basically a longish list of examples of what can be done. So as I said, a couple of definitions initially. One is the threat model. Is essentially the premise of any attack is to say what exactly are the characteristic of this attack. What is the trusted computing base? So what is the hardware and software components that are supposed to be trusted? What security properties, we'll discuss this in the next slide, this computing base is supposed to guarantee, like confidentiality, isolation between two users, and so on and so forth. What we think the attacker can be, what we assume the attacker is capable of. Can he run software on our machine? Can the attacker have physical access to my DRAM chip in my circuit, and so on and so forth? So what are the possibilities that I suppose the attacker has? And of course, what is the conclusion that it can, what is the result of the attack? What can the attacker gain of my system? So I will try to be to list the critical parts of a threat model in the presentation of the different attacks. I will not do it very systematically and maybe not as precisely as people expect people to do it in security papers. In fact, I think also there are a few papers that usually miss a good precision of the threat model, but I'll try to always make relatively clear what are the attacker assumptions that we have, and of course what are the security properties that we think an attack is going to break. And security properties, if you have taken any other course in security, you'll see that there are a lot of discussions about which ones are the fundamental security properties, what should be included or not. I'll stick to maybe the most classic and simple model. We want to protect confidentiality, that is, we don't want to disclose secret information by one of the parties. We want to make sure that the protected information is not modified by a malicious attacker. So we want to guarantee the integrity, and we will never probably discuss about this, but in general, there is also the availability, the fact of guaranteeing that services and systems remain available to legitimate users and are not made unavailable maliciously. So we will speak essentially of confidentiality and integrity, and there is maybe one more concept that we will use, which is the one of isolation. In fact, I mentioned already isolation, which is the ability to prevent any interaction between different processes running on the same operating system or on the same processor, or different users exploiting, so using the same computing equipment. And isolation is actually the way typically we guarantee architecturally confidentiality and integrity, in the sense that we are going to use the same registers and the same data path, but by making sure that I cannot read your register R3, you will not leak your system, your secret, and the fact that I cannot write, I have no way to write into your register R3 will guarantee you integrity. And this is exactly what it will break, is that indeed I cannot write into your register R3 or cannot read your register R3 directly, but I may be able to read something else that is not addressed in the architecture, so is not by construction protected. The isolation is not guaranteed because we don't know that it exists in some sense, and from there I'll learn secrets, or maybe even be able to manipulate secrets. Before we move to these side channel attacks that correspond to what I was just mentioning, there is one attack on memory that has gotten a lot of attention in the last few years, that is actually one that compromises integrity, makes it possible to modify your secrets. It's called Rowhammer, and before we go there, we need to make a little reminder about what is dynamic random access memory. Now, dynamic random access memory is maybe something we never discussed very explicitly in this course, but is one very important component of our computing equipment. DRAMs are the densest form of random access memory that exists. It is therefore, because it is the densest, is also the cheapest, and has been one of the critical components to the progress of computing systems. The ability of having today up to terabytes of memory available online to a computing system has been at the heart of a lot of the progresses of computer science in the last decades. And DRAMs are a relatively, I would say, weird idea. Instead of storing information in appropriate logic circuits with memory, like D flip-flops, for instance, right, where you have one component that memorizes one bit of information. Instead of doing that, and instead of doing what you do in SRAMs, static RAMs, which are essentially qualitatively large arrays of D flip-flops, of these logic systems memorizing information, DRAMs is essentially a purely electric way of memorizing information by taking capacitors, small parasitic capacitors that originally you may not have wanted, but now you try to make these parasitic capacitors big enough so that you can store charge on them, and the presence or the absence of charge on these capacitors represents your information. It represents a 1 or a 0. It's a very old component. The first patent in using transistors was in 1968 by a guy named Robert Dennard, and many of you know some Dennard law, scaling law, which is named from exactly the same person. And they scaled incredibly well over the decades. I said it already, they are one of the key components, one that we tend to forget because it's not as fancy as our processors, right? We spent weeks at the beginning of this course to look at how processors have evolved with incredible nice ideas. This is a component that has just been improved technologically to become smaller and smaller and smaller. And I say it is a very weird idea, because one of the problems is that the charge that I use to store the information naturally leaks off the capacitance of the capacitor, because there are parasitic resistance. There are not only parasitic capacitances, but also parasitic resistance that simply discharge, make these electrons move away over time. So our information is extremely, how can I say, perishable in a DRAM, and it needs a huge machinery that essentially goes back to every single one of these bits of information very frequently, multiple times per second, to do what we call a refresh, that is to read this information, look how much charge there is on a specific bit, and replenish this charge. So if there was no charge, there is no charge, but if there is a bit of charge and is not the complete amount of charge that we put, but less because it has leaked off, we are going to replenish it and put it back in the bit. And this we are going to do for those gigabits, terabits of information that we have all the time, multiple times for a second. So in a sense, you can say, oh my God, is a completely crazy stuff that will never work, or nobody will ever want to do it. In fact, it has always been used, and it is extremely important, is used essentially for main memory, the main memory of our systems, because it is cheap. So it's where we want the largest amount of memory. We put this. It's clumsy, it's slow to operate, so we put caches in front of it to try to compensate for the, let's say, poor technological characteristics, but it's omnipresent, right? It's one of those things that I don't think I know of any system of some importance where there is not a large amount of DRAM in the system. So what is the phenomenon that leads to this potential attack? The fragility that DRAM has is that these transistors, these capacitors are extremely small and extremely packed together. They are always organized in a two-dimensional array, of course, because we need to place them on two-dimensional chips, and they are typically organized in rows or wards, and they are connected, the different cells are connected by bit lines. You can have a very simple understanding of how this normally works, is that you have this transistor, and you can always think of it as a transistor as essentially a switch, something that is open or closed, and these transistors are all normally open, so that these capacitors are isolated, they have their charge, and it stays there, at least until it leaks away. And as soon as you select a word, or you select a row, if you prefer, you close all these transistors, and you start discharging this capacitance, if there is charge over it, through the readout circuit that is called a sense amplifier. In a sense, you are connecting it with something that, if you want, measures the potential that is on the armature of this capacitor, and therefore determines whether this was a 0 or a 1. And it's usually a reading that is destructive, in the sense that when you read out, you lose the capacitance on the capacitor, therefore you lose the information, but you read it, and now you can write it back to have it there for the next reading. And so one of the problems that you can have are all the problems of capacitive coupling. For instance, you have these rows that are maybe relatively long, and they are all parallel, and therefore there is a capacitance between adjacent word lines, and they tend to influence a bit each other. Now, this is normal business somehow, in the sense that every real circuit, every VLSI circuit that is implemented has some problems of noise margins and so on, that are controlled by making sure that the capacitance between these two is not enough to make to activate these transistors when these transistors are activated. Except the problem is that you can have this reliability issue that is never going to be sort of zero, is never going to be uh, uh, completely absent this phenomenon of influence between neighboring world lines. And it may be that if things are not computed or predicted in the manufacturing exactly precisely, maybe this noise margin in some cases may not be enough to guarantee this from malfunctioning. In particular, if you have the accesses, continuous accesses to two word lines neighboring a third one, so on the two sides of a third one, maybe what is going to happen is that apart from keeping reading these two rows, what might happen is that somehow by capacitive coupling, this word line is not really activated, but gets a little bit of potential growing. The potential that grows would slightly start to close these transistors. They will not necessarily close, or not really close like in a real reading, but somehow will leak off more easily the quantities that are in this capacitor, and maybe this capacitor that had a charge will leak the charge before the next refresh, and therefore what was maybe a 1 will now look like a 0. Now, disturbance errors, these are called disturbance errors in the sense that you can disturb a cell by the environment. Again, are a design issue that is typical of any circuit, and has been known as one of the parameters in the design of DRAM since ever. Except that there may be the packing of these devices has become so tight that ensuring sufficiently good design noise margin has become extremely difficult. And since we are talking of billions, literally billions of access transistors, maybe some of these access transistors will be a little weaker than others and will leak more easily than others, and therefore it becomes even from a statistical standpoint more and more difficult to ensure that no disturbance errors will ever affect our device. Or maybe even my expression is incorrect. There is no way to ensure that it will never, but that the probability is below some extremely low level. Whether we are above or below this level may be extremely difficult to guarantee. And this is the attack that people have been thinking of, different groups more or less around the same time, which corresponds to what I was suggesting a second ago, which is to continuously read two variables or two locations in the DRAM that corresponds to two almost adjacent array, or two rows that are adjacent to a third row where I have my critical information stored. And by continuing accessing this one and this one all the time at the highest frequency that I can, you see here, move, jump to the beginning. So I do read and read. They are reads from memory to the register. This is x86 syntax. I go and read something from one row to the other row, and I repeat all over all the time. The hope is that one of these cells that are in the middle will be compromised. It will go from 1 to 0 or from 0 to 1. And you see the code is only slightly more complex because, of course, if I try to do this from my x86, there is a cache in front of it. And so the cache will get the first value of the move and will keep it. And so the second move will come from the cache and not from the DRAM, which will prevent my attack, my attempt to break the DRAM functionality to work. So I need to do a cache line flash, which is a standard instruction that is available to every user. Is an unprivileged x86 instruction to flash something from the cache. So I need to flash the two quantities that I've just been reading so that they will be read again. I need to put a memory fence to make sure that this is really done. Essentially, I need to wait for the cache to be flashed. But apart from these, call them details to make it really work, to make my move do it, it's extremely simple piece of code. I'm just trying to read two things, and which are, I know, located neighboring to some other piece of data that I'm interested in, and I hope that this piece of data victim will change. Now, one of the interesting things is, okay, so this is a way to make the memory not work. Can I gain something from ruining the memory of potentially someone else, and can it be the memory of someone else when it is probably so close to me, right? Sort of, I am in different rows of the same memory chip. Depends how the memory chips are addressed in the system, but probably the owner most likely of these capacitors, of these bits of information, is the same owner of these bits of information. So is this going to be useful for any practical attack or not? Essentially, the key for this, the possibility of an attack, is to realize that we violate memory protection essentially in the following form. If I have an area of memory where I can only read, this gives me the possibility also of writing into this memory area. And therefore, people looked at what are data structures that I typically have in readable form, but where I cannot write, and therefore by writing maybe I gain something. This is the typical structure of an attack that has been demonstrated with Rowhammer, which is to start by looking and understanding the which cells of my physical memory are actually weak. And the way, so first of all, the observation that I made already before, these are physical properties that depend a lot on fabrication of individual capacitors. Some capacitors may be a little bit smaller than the others around them. Some transistors may be a little bit weaker in the sense that they may have more leakage, induce more leakage at the same potential applied on the gate, something like this, right? So there are manufacturing variations that make what is essentially a good and safe DRAM unsafe in only a few bits. So the idea is that initially what I do is that I allocate a lot of memory. Essentially, I fill the system with memory that I obtain from the operating system in legal ways. It's completely memory that is available to me, so I can do whatever I want, and I do all my tests basically based on this Rowhammer attack to understand which cells in this in the physical memory that I have are weaker than the others. Then I release all the memory and all done, but I have now an idea of what I can make fail when I need. The key idea related to what I was saying before is that I can now write, or at least I can flip randomly bits or semi-randomly bits in area of memory that I'm given read-only by the operating system, is to realize that you can get a lot of these kind of structures when you take a file and you open it many times with read-write permissions. And when I say many times, I mean a gigantic number of times in such a way that the operating systems will be forced to create, to fill essentially the complete memory or a large parts of memory with page table entries, with the translation tables that will go from the virtual address that I have for my buffer for reading this file, translation in physical address. So since I open it many times, I have many virtual addresses that I can use to access essentially the same physical location that is a buffer that somewhere the operating system has created for this file. And typically the buffer will be created only once in memory, but there will be all these translation tables, all these page table entries that are repeated for each opening of the file. Now that I have my memory that is essentially full of page tables, they are exactly what I wanted, because I can read, typically in operating systems, I am allowed to read them because basically they are used to translate the physical page into the virtual pages into physical pages for my file. And therefore, I can go and read them and play the Rowhammer trip to flip something. What happens is that, so the something that will flip is random, but if I'm a little lucky, what will happen is that one of the page table entries after I've done my Rowhammer attack will now point somewhere else in a different physical page. So instead of pointing to my file, will now point somewhere else in memory. Now, since I filled up memories with page table entries, chances are that it points to one of these pages in my memory where there are page table entries. Now, the operating system that doesn't know anything about this flipping will think that by accessing something through this page table entry, I will be accessing the buffer of my file that is open for read and write. So I can read and write at the destination of this translation from the page table entry, except that now it points to another page table entry. Aha. So now I can read and write legitimately other page table entries. So if the first flip was random, I don't control very much where it lands, right? I just am happy, and this is the only thing that I need, is that it lands on a different page table entry. But now I gain read-write access to this page table entry, and now I can write whatever. I don't need to be lucky. I can write whatever I want in this page table entry. And by going and using another of these accesses to my file, I will go through this page table entry, and basically I will be able to read and write what my operating system thinks is still the file and the buffer of the file, but in fact I'm reading and writing anything else in the physical memory. So it is a very, very powerful attack because it gives basically memory protection is completely gone, right? It's not so simple. There are a gazillion of problems in making it work. From well, every sort of difficulties that if you try to imagine how to implement it, you'll realize that there are difficulties all over the place, but thanks to typically also some other attacks that are well known, or some other methodologies of attack that are well known, in the end, people managed to get this completely to work. And once more, it's an extremely severe attack because it destroys completely all the system of memory protection. So it's actually initially an integrity problem, an integrity attack. You modify a bit of memory, but in reality, it's relatively easy to turn it into a confidentiality attack or a integrity attack, because you can get access to the secrets, and also you can modify the data of someone else, but not only in the random flipping, but once you have access to every part of memory, you can do every sort of damage and modification in the data of someone else that you wish to do. It will be relatively a leitmotif of today is that the mitigations are not brilliant. People have been looking a huge lot into different ways of doing the raw hammer attack and improving it, as well as finding mitigations. But the point is, there are not great mitigations unless you change something relatively heavily in your system. So if you want just to mitigate it in a system that is susceptible of this to these kind of attacks, there is not much that you can do. Error correcting codes, essentially, first of all, they are not switched on in every system, but if your system is using error correcting codes may not be good enough to detect some of these raw hammer induced effects. For instance, there is usually a correlation between the fact that you can affect some cell and the fact that you can access the various cells in that row, typically because maybe the two rows are a little too close, have a capacitance that is a little bit higher, so the crosstalk is a bit higher. So you don't impact only one cell, but you can find easily rows where you impact multiple cells, and impacting multiple cells typically escapes the ability of error correcting codes to detect that something is a problem. The one thing that is not a solution, but certainly has a clear impact in reducing the probability of a raw hammer attack, is to refresh more often, right? You reduce the interval between two refreshes, and the chances that the cell loses completely the charge or loses sufficiently charge to be affected by raw hammer goes down. So one of the things, one of the mitigations, the most effective that people could do on legacy systems that needed to be secured against raw hammer, has been to change the firmware and program all the logic that does the refreshes in such a way to do a refresh more often. This comes to a cost, of course, right? Because refreshing more often typically means more a significantly higher power consumption, because you discharge the cell and you put back the charge, which involve consumption. So if you do it twice as fast, you'll have a significant increase in the power consumption, and will have a performance impact, because clearly this refresh business impacts your ability to read. While you are refreshing a specific array of DRAM, of course, you cannot do something else like reading something that you're interested in the DRAM. So if you do it more often, the chances that it collides, there is a collision between your attempt to read and the refresh increases. What can you do if you change the DRAM? I think it's an interesting question, and especially the answer is particularly, I find interesting, is that, of course, the natural thing to do is to say, okay, but this is a disturbance problem that depends from the fragility of my circuit. My circuit is too fragile because I put the cells so close, I made all my capacitances so small, and so on and so forth. So maybe we relax some of these design parameters. Now, of course, this costs a lot, right? Because the moment I try to improve the electrical behavior of my circuit to withstand this kind of attacks, I make everything bigger, and everything bigger means that I am no longer able to do those gigabits of DRAM for $1. So I lose a lot of money. And what the manufacturers of DRAM has done is something maybe more clever, but I find it interesting as a reaction, because it's really not trying to fix really the problem, but try to detect the problem and do something architecturally that protects from the problem. And the idea is to detect the fact that some rows have received a high number of activations within a time window, sort of create some structures in the DRAM chip that counts and checks how many activations there are. And if they are a bit too many, then maybe there is an attack on the neighboring on the neighboring rows, and therefore we go into these neighboring rows and we do a refresh, so that if they were being attacked successfully, if we were close to lose the information, we rewrite it with an additional refresh on top of the natural and normal refresh, so that they don't leak anymore and the problem doesn't exist. It seems to be very efficient and very effective in reducing the problem. It's implemented in some of the DDR4 products, for instance, although it is not part of the standard. And maybe for now, it's a solution in systems that are sufficiently modern to have this kind of products, a sufficient solution for this attack. Before abandoning DRAMs, I think it's interesting to see that one could also use the opposite side of the same story, or in the following sense. What we have seen depends on the fact that we store information on these capacitances, and it may be possible to make some of these cells leak the information faster than it would naturally do. The other thing that one could exploit to attack a system is the fact that there are also particularly good cells that maybe store and keep the information for much longer than they are supposed to. So it turns out that basically what you can do is that you might switch off a system and maybe switch it on again with a different operating system, or with a memory test, malicious memory test software, and you might figure out that you find some of the information that has not disappeared. So it is supposed to be leaky, it is supposed to disappear after 60 milliseconds or so, but in fact this is only a worst case scenario. Maybe not worst case enough for the raw hammer attacks, but a worst case scenario in normal operation. But then there is the best case that maybe it lasts the information seconds. So I have the time to reboot the system and go and read the secret of the user before I switched off. And worse than that, there are, given the fact that we are talking of physical phenomena, I can delay them. I can delay the leakage because I reduce the mobility of the electrons by freezing the DRAM. So I can use spray refrigerants that are available all over the place because they are used even for legitimate debugging of circuits, and I spray over my DRAM chips. I switch off a system that contains secrets that I cannot access via software, and now I reboot. I reboot with an operating system or a monitor that goes and reading these chips, and I read essentially the complete or almost complete set of informations that were in the chip, including passwords, secret keys, or all the beautiful things that I may find. Let's move now to these side channel attacks, and let me define what side channels attacks or side channels in general are, starting from the notion of covert channels. So what is a covert channel? The covert channel is an intentional mean of communication, but that uses something that has not been designed to be a communication channel. So I have two parties that communicate some information, but don't use anything that has been originally conceived as a medium of communication. The typical situation where this is used and developed is to have inside a critical or a victim process something of the attacker. It's usually called a Trojan horse that by some mean I managed to infiltrate in the victim ecosystem and gathers being there some of the secrets, and then sends these secrets to me in ways that are not observable by the victim, either exactly because I don't want to be observed while sending this data. I don't want to send packets somewhere because someone will observe and notice that there are packets going in a place where they should not be going, or because there is really no media between the two because of the isolation, and therefore there needs to be another way of creating communication. We will not discuss Trojan horse or covert channels in this course, but we'll discuss side channel attacks that are a form of covert channel, but where the sender is the victim, and the victim sends out information not by doing something specific for sending the information as in a covert channel, but in a normal covert channel, but because of the normal operation of the victim, unsuspectingly, it will be leaking information that I receive on the other end of the covert channel. You'll see very much more clearly through examples what this means, but basically if there is the victim that is using the cache to do the accesses that it needs to do on the cache, maybe by my using the cache, I can receive as an information something that the user has leaked unwillingly. So it's sort of, there are two ways of looking at this, or two classes of this leakage process. One is where the sender or the victim, depending if you look at the covert channel or the side channel situation, the sender sends information through the system state. Is what I call these microarchitectural side channels, is because there is the cache, there are branch predictors, there are pipelines, there are something of the state of my system that reveals information, gives information to the receiver. Note that this almost always and intrinsically microarchitectural, because unless there are bugs in the way the system is implemented, if we are not meant to communicate, the architectural state of the system is not shared. Is what I mentioned before, what we can take from the example of Rowhammer. If there is a memory protection system that is working between two processes, if one of them marks the memory as being protected and not readable by someone else, the other one cannot read it because it's correctly implemented. And this is the memory, the DRAM, is the architecturally visible state. What here we are going to use systematically is the microarchitectural state, which doesn't exist, is not considered observable ever in any case, and so is never protected in practice. And that's exactly why all these types of side channels work. The other one, which if you remember, I already described before today by saying the other possible channel is that the sender, by operating the system, does have some physical emanations of the from the system. The system will heat up, will emit electromagnetic waves, will use some current from the source of electrical energy that powers it. And all these physical emanations can be used by a receiver, typically through some measuring instruments. So usually there is a need of physical presence of some sort around the victim to gather these some physical effect of these emanations and use it. Maybe we'll see also some examples where there is no need for physical presence in some very peculiar cases that are starting to emerge now. So today is about this bottom layer, the microarchitectural side channels, and we will discuss physical side channel in 2 lectures. I think I said already almost everything that is on this slide, maybe except one thing, which is observing the fact that the source cause of the problem in microarchitectural side channels is the fact that we are sharing hardware components, right? If we had physical replication and complete physical isolation, we will not share microarchitectural state, and therefore there will be no problem. Two processors that have their own level 1 cache will not leak anything through the to each other through the L1 cache because the microarchitectural state is not shared. But the fact is that we do share a lot of microarchitectural state between processes, users, operating systems, maybe in hypervisors, and this is why the microarchitectural state opens up for side channel attacks. We'll now see the first and maybe simplest form of side channel attacks, the timing side channel attacks, which are not necessarily linked to microarchitectural state. It's one problem that is typical of how even we write software. The classic, this is one of the classic examples. I think it comes from Wikipedia, but it's probably one that you find in most of the literature. Is that we write software naturally in a way that typically has an early return and early termination in case we have already the answer to the problem. It seems to be, if you want, healthy programming, right? You see here that we are doing a comparison between two strings A and B, or CA and CB, and as soon as we find one character that is different, we can tell that the two strings are different and return. Now, the disadvantage of this is that, or the problem in terms of security of this is that it means that we return after as soon as we find the first different characters. And so if some attacker can observe how much time we take into this comparison, can tell how many characters were correct and where is the first character that is wrong. So imagine that, of course, this is not the way you would implement a check for a password, but imagine that this were the way. You can tell from the length of the this string compare how many characters are correct, which means that essentially you from an exponential complexity in checking, in guessing a password, you go to a linear complexity, because one by one you try to guess. When you're ready, you guess the second one and the third one, and so on and so forth. So there is a very simple mitigation for this, at least on paper, which is to write software in a different way, in a way that is, in most cases, unnatural. Is not what we would write, because again, it has a bad impact on timing by making the timing essentially the worst case, always the worst case, where here we continue to check the different characters, updating a variable that is the result, that is the end of all the checks. And if one of them failed at the end, but after checking all the characters, we return the result. Now, so it's a very simple type of situation, very common because we write code normally in a way that is terminates early if it is possible, and therefore naturally reveals potential secrets, but it's also very simple, at least superficially, to try to correct the problem by making our problems not, by our programs not data have a timing behavior that depends from the data. In practice, it's not always so easy. One of the problems that one encounters in doing this is that you are essentially fighting compiler optimizations by doing this. It's clear that the way we get from a early termination kind of program, a faster program, to a worst case always program is by doing computation that is not needed, or wasting time doing stuff that are not needed. So if I have a compiler, and maybe luckily my compilers are dumb enough not to see it, but if I have a compiler that is smart enough to see what I'm doing, it might optimize out what I've done, and my program, even written apparently to computing constant time, actually will be leaking again once manipulated by the compiler, once processed by the compiler. Also, there may be some microarchitectural phenomena, and this is where our interest for all this comes in the picture, is that maybe instructions have a variable latency. So if I do a div, maybe my div will take longer or more time, depending on what is the dividend or the divisor. I have caches that will hit or miss and therefore have a different timing behavior. This is the class of things that we are interested in. So besides the fact that you could write your software in a way that it has blatantly varied execution time, we're interested when this is not the case, but you still have variability. And you'll notice that most of the attacks that we'll give different names to, like cache attacks, are intrinsically timing attacks, but on very specific microarchitectural phenomena that determine a variable execution time. So let's get started with this one, with the side channel attacks through caches. Cache side channel attacks are one of the oldest form of attacks. It has been evoked since 1992, but it is only at the beginning of this millennium that people really managed to do it. The advantage is that caches are always shared between processes. I'm not thinking yet, we'll discuss this later in terms of different cores sharing the same cache, but I'm thinking of a single processor that has a cache, and every user of the processor, so every process that is loaded every 100 milliseconds on the process, uses it and goes away and is replaced by someone else, shares the cache with the other processes. The key idea, I think, is clear, is that caches behave in two ways. I can have hits, I can have misses. They are very different in terms of timing. So if I have a sufficiently high resolution timer methods for measurement, I can tell whether something is a hit or a miss. And my victim might either evict something that I put there, so what should be a hit becomes a miss, or I can find quickly something in memory, and so that indicates that something was accessed by the victim. We'll look at some of these different arrangement, but the point is always the same, is that I can differentiate hit and misses with a high resolution timing measurement. And the key point is that knowing where the victim has done loads and stores, so I'll never access the information that is in one of the locations where the victim does the loads and stores, but I will know where the loads and stores or stores have been made. This fact will give me secrets. You have here a couple of examples that we will see in the coming slides and in the coming attacks. Practical demonstrated attacks is, for instance, the fact that accesses in the data cache may indicate the secret. For instance, if I have a SBox that is part of the implementation of most cryptographic algorithms, and I implement it as a lookup table, by figuring out which element in the array of this lookup table has been read, I know something. I may discover something about the secret key. The leakage is not only on the data side, by looking exactly at which accesses have been done by the program and where the program has read in arrays, but also in the instruction side, which parts of the program the victim has read. For instance, I may learn something about the RSA encryption that I'm doing and the key that I'm using in doing the RSA encryption by looking at which parts of the code have been run given a specific encryption to be made. The assumption that we made initially, but we'll see that is not necessarily the case, is that the attacker can run the victim code, can do, for instance, an encryption or a decryption whenever the attacker wants, which seems to be a very strong assumption, but maybe is not, right? For instance, if I want to discover what is the key encryption and decryption key of a volume that is mounted on my system so that I can go and read the secrets of others from that disk, it's reasonable to assume, or it certainly happens that I can access the encrypted volume for my own files, and therefore I can open a file and I can write my own data in the disk whenever I want. And if this gives me access, allows me to learn the encryption key of the volume, then I can use this encryption key to go and decode the data of the others. Similarly, for instance, if I want to learn the secret key of a VPN, but maybe the VPN is available to all the users of the system, so I can just use the VPN to send messages and therefore force encryptions whenever I want, and through that learn how to break completely the VPN for all the other users. So here is the first example that we are going to see of these kind of attacks, and it answers the question, has the victim accessed a specific location? And when we say a specific location, since we are talking of caches, the resolution of our localization of things is always a cache line. So whenever we say location X, what in reality mean has accessed a location inside a specific set of the cache or a specific cache line in the memory. Before looking into the evict plus time attack, let's remind ourselves a bit of how caches work, and maybe let's clarify the representation that I'm going to use today for the rest of the day. So caches are composed of sets, is what I just alluded to, or if you want cache lines of data, typically maybe 512 bits, so several bytes and several words of data. This is the elementary resolution of the data that is in the cache. And the way we put things in the cache is that we use some bit of the addresses to address one of the sets. In this case, there are 8 sets, but there could be, in general, many more, and of the order of maybe 256, 512, 1024. So we choose with some bits of the address in which set to put the information, and we put the information in one of these rectangle. Unfortunately, there is aliasing. If I have two addresses that I'm interested in that have the same bits, those bits that I use to identify the sets that are exactly the same, they will be we say aliasing, that is, they will be competing for the same space in the cache. So what we do is that we have several ways. So we replicate the same structure multiple times, and we put each piece of information in one of these completely equivalent locations. So this is what we call a set associative cache. If there were only one of these columns, it would be a direct map cache. If there were only one set and everything would be associative, it would be a fully associative cache. Practical caches are a compromise between these two words, typically with a relatively small set of associative structures, so 4, 8, maybe 16 in some cases. The compromise is determined by the fact that the more the associativity is high, the more ways there are, the more comparisons there will be to do, the higher will be the cost, the more power consumption the cache might have in many practical settings. So typically the number of sets is the number of ways is reduced to a minimum, and yet not so small as to have too many aliases, which will imply a lot of misses. Now, I hope all this is clear to you because you remember caches. If for some reason you are not completely clear what I'm representing here, what are these ways, what is set associativity, what are sets, and so on, I invite you to make a little break and go immediately now to check your background on caches, because whatever we'll do will depend very critical on understanding how a cache exactly works. So if we are clear about the cache, how does this evict plus time work? So again, the question that we ask is whether the victim has accessed a specific location that is in one of the set, right? So what we do is that we start by running the victim. Again, the assumption that I said before, we can start and have the victim do an encryption of a specific message that we want, and it will touch a number, it will access a number of locations in memory that will bring in memory, shown here in gold, different sets that are now in the cache. We'll do it again. We'll run the victim and do exactly the same encoding with the same data, which will be very fast because, of course, all the data that it requires are now in the cache because we just ran it and we didn't do anything in between. And we'll time it. So we'll see how fast is the victim to do this encoding given that everything is in the cache. And now we are going and take the set that we are interested in, the set that we want to ask whether the victim accesses this set. And what we're going to do is that we are putting our stuff there. We are going to read a data structure or some data structures of us that exactly put data only in all the different ways. Now, one of the things that is important here and is maybe not completely trivial, or at least needs a little bit of information on the cache to do properly, is that we need to put our information, the attacker needs to put its own information in all the ways of the cache. So, for instance, we need to know what are the number of ways, or at least have a worst case information about how many ways there can be, because we need to try to cover them all. If we don't manage to put our information in all of the ways of the set associative cache, whatever we think we are doing will actually not work very well. Now that we have taken away the information by construction, taken away the information of the victim, we run the victim again and we time it again. And now there are two things can happen, right? Either we have exactly the same time that we had at the step number 2, which means that all the accesses that the victim does are hits, and which in turn means that the set that we are targeting, the set Y that we have been evicting, doesn't concern a victim. The victim doesn't access this set, and that's the answer to our question. If, as I said, the victim runs exactly in the same time, or the victim will now have some misses compared to when I did it before, so it will take longer time because we just evicted some of the data of the victim, and therefore I'll detect the fact that the victim actually accesses the set that I've been polluting. Okay, so it works, right? I take a measurement of the execution time of the victim in the situation that I construct, where I know that the victim will have only hits. I pollute somewhere in the cache, and I see if this has an effect. If it has an effect, I have been taking out some information that the victim accesses. One of the problems of this system is that it relies on measuring the precise execution time of the victim. Now, this may not seem to be a problem at first because, of course, we are doing exactly the same execution. We are calling it within the same context. We are doing exactly the same, for instance, encryption if the victim is encrypting and we are looking for the secret key. So there should be no variability in the executed code. The problem is that there may be some environmental issues that we don't control. Are there, for instance, system calls or interrupts that are happening in the middle of the code? Are there some other microarchitectural phenomena that take place that we don't control, like branch prediction is less effective the second time that I run the code because something else has happened in between? Or maybe because of similar reasons, the scheduling of the instructions, that is the way they go through our reservation stations and reorder buffer, is different. It may be small noise, but it may be comparable to this hit versus miss, which is only a few, maybe a few tens of cycles difference. It may be enough to obscure the result. One way to fight this that we will see will be a leitmotif of many of these attacks, of the reduction of noise of many of these attacks, is to repeat the attack many times. If I re-encode many times and I do the same analysis to see if the timing has changed or not between two executions, well, maybe once I'll be unlucky and I get a system call, but I will not get the system call every time. So after a while, I will get statistically some information that I can really use. Here is an example of what I may expect from this. Is from the original paper that demonstrated that these kind of cache attacks are feasible and are useful to actually really learn from real code the key of an encryption. You see here many measurements that have been done for testing different addresses under different plain texts that have been encrypted through a public library that is the library of the victim. So we don't know the secret key, but we can encode whatever we want and probe as many times as we want what our victim has accessed. And here you see the timing. So where the timing, the lighter timing means that is a slower timing. So it is a miss essentially in the code. And you see that this gray is relatively uniform if you see if you look at this figure from far away, but actually individual measurements are affected by a considerable amount of noise. Still, the noise is not enough not to let you see that there is a very specific pattern here and here between the plain text that you gave to the encryptor and the addresses that have been accessed. And this is exactly the data dependence accesses to the SBox that I was evoking a little earlier. And you can show that this tells us something about, tells a lot, in fact, about the secret key. Now, another type of attack that people exploit and have been building upon is this prime and probe. That is actually potentially a much more general type of attack that answers the question of what are the locations or what are the sets that the victim accesses. And this time we are going to prime the cache before running the the victim. And by priming, we mean like sort of painting preparing all the cache by filling all the sets in all the ways with our own content. And then we go and read every piece of data, or actually all the sets of data, and we time how much it takes for us to read any of these sets, and which is going to be fast because of course we just put the information, so we are getting only hits from the cache. And then we are going to run the victim that will taint, that will pollute some of our information depending on the accesses that the victim does. And now if I go and I probe, I read all the data, all the pieces of data from all the sets, and I time exactly like I did at step 2, I have the same kind of sort of measurement of information that I had before in the previous attack. If the time doesn't change, it means that the victim didn't evict some of my information, so did not access that particular set. If now I take longer, is because I have some misses. If I have some misses, is because the victim has evicted my information. If it has evicted my information, is because it has accessed that set. And so I can create a map and know exactly which accesses have been done. And you have it here, is essentially the same kind of information that we have seen before. You see that the kind of noise that you have is slightly different. But one key advantage that you have here is that you have more control of noise, because if you go back and you think of what part of the execution is being timed in a crucial way. Now what you are timing your code that reads the different sets. Whereas if I go a little bit back and I look at what I was timing in the evict plus time, what I was timing was the victim. So instead of timing something that I don't know of too much and I have little control on, and maybe is not a nice code with a lot of uses of branch predictors and so on, and so I make myself dependent from that, now it is my own code that I write. So maybe I can write this code in such a way that is particularly robust to some of the phenomena that might create noise. So typically you can do less repeat accesses to achieve a better quality of information from prime and probe. Okay, so we have seen two of the classic ways to access the information of your victim, of which accesses your victim has done. As I suggested already a few times in the previous slides, in cryptographic algorithms, having an information about which accesses have been done is key in discovering something about the secret key. So you have here some score, some sort of metric that gives you a sense whether you are hitting the right key or the wrong key. And here from the same paper that was doing the two previous attacks that we have just seen is what is the score around different possible key hypotheses. And what you get from this is that there is a clear cluster here that says that the key is between 80 and 96 is an hypothesis that is significantly better than the others, which in other words means that the first half byte of my key is 5, and I learn part of the secret by doing all these attacks. We've seen a couple of cache attacks that worked successfully to discover the secret of a victim that we could trigger whenever we wanted. Now we can start asking ourselves some questions, and in fact understanding a little bit more how these attacks actually could be successful by looking at what can we do, for instance, with large caches. Now, why large caches will be a problem? To understand this, we need to remind ourselves of how addressing of the caches happen. That is, what is in between our deciding to do a specific load and the actual address that is sent to the cache. Modern caches are almost universally physically mapped. That is, they don't see the virtual address, but they see the physical address. Whatever we use when we do a load is by nature a virtual address. So what is in between? We have to go back to our undergrad course and look at what is the structure of the classic translation. And once more, if you are not clear about these things, please make a pause and go and revise your undergrad virtual memory courses. But most practically all modern systems do the translation based on pages. That is, memory is split in chunks that are called pages, and when we issue an address is made essentially of two parts. One part that is the exact position inside a page that stays unmodified between the virtual address and the physical address, and the number of page, which page are we addressing, that is the part that get translated, and get translated arbitrarily through the page table. So I have some virtual page which corresponds to the high part of the address, which gets into the page table and gets, as I said, arbitrarily translate into a physical page. And of course, the virtual page and the physical page, despite what we see in this figure, are not necessarily the same size. Maybe the virtual page is much bigger and the physical page is smaller, but this is completely irrelevant to us. What is relevant to us is that we may not be able to know, and in general, we are not able to know, what is the physical page that corresponds to a given virtual page. We ask pages from the operating system, and the operating system says, okay, this address is now available to you. So we know that we can use a specific virtual page, but we have no idea what is the physical page or the physical address that corresponds to a specific virtual address. Except, going back to what I was describing a minute ago, for the last few bits. And these few bits are the offset inside the page. So if I have, as typically I have, a page that is made of 4096 bytes, that is 2 to the 12 bytes, it means that I have 12 bits of the address that are guaranteed to be the same between virtual address and physical address, and everything else that is unknown to me. There are some attacks that help me discover the physical translation, but they are not always applicable. So what we assume is that I know nothing of this part, but I know everything of this part. Okay, so this has some limitations on what I can do on caches now, right? Because now if I look at how my caches are addressed and how I use the different bits of the cache, I land into qualitatively different kind of situations. So let's look again how I use the bits, the addressing bits in the cache. And I already mentioned this a few slides ago, right? I have sets in the cache. I have cache lines in the cache. That is, I handle groups of words instead of individual words in the cache, and which means that I take several bytes together, or several words together in the same location in the cache. So for instance, a typical um, caches these days have 512 bits in a cache line. 512 bits corresponds to 64 bytes, that is 2 to the 6 bytes, which means that 6 bits of the address are used to identify which part of the cache line are we actually addressing. So this is the offset inside the cache line, which is not particularly interesting for us because is what we said before is the resolution of our cache attack is that anything within a cache line, so any difference in these bits has exactly the same effect. Either I hit or I miss on the cache line, either I replace or I leave the same one inside, but they are essentially, in a sense, useless. And then there are a few other bits that I was evoking before, which corresponds to the selection of the set that I am considering for placing this information, the corresponding information in the cache. That is the index bits that are used to address the cache. So remember before we had this example of the cache with 8 sets. I need 3 bits to address 8 sets. It would have been a cache with only 3 bits of index. Now, the qualitative difference between different caches that I could build is that if I have very few bits of index, the index plus the cache line offset may be within the page offset. That is, within the number of bits that I can control from my virtual address. If this happens, you understand that I'm lucky and happy, right? Because now by issuing a virtual address, I control completely what happens in the cache, because all the bits that I don't control are actually completely irrelevant, are parts of the cache tag, which is nothing to do with what I want to do, evicting, checking hits, and so on and so forth. But if my cache is such that some of the bits of the index are outside the offset of the pages of the virtual memory, they are not controllable by me. So if I'm in this situation, everything is fine. If I'm in this situation, I may not be able to do a cache attack proficiently, or at least I need to do something else. Now, this is a situation that is almost guaranteed, this qualitative situation where the index and the offset, cache line offset, are inside the virtual page offset, is a situation that is almost guaranteed to be true for L1 cache. I may actually even do one of my poses for you to think about it, because you should either know or be able to imagine why this is an essential feature for a level 1 cache. Actually, let me do the break, right? Why am I sure that in any practical L1 cache that I have, these bits are always within those bits? And in fact, because I like to have large caches, so I want to have as many bits in the index as I can afford, I always have, if this is 12, I always have these 6 bits, so exactly 64 sets in my cache. Why is that? Why I don't have, instead of 64, 128 sets? Well, it's easy. the reason why this happens is that I need to access L1 very fast. Now, if some of these bits of the index spill in the part that is translated between virtual page and physical page, if I want to access the cache, if I want to go and read the index, what I need to do is that I need first to translate the virtual page into physical page. That is, I need to put the virtual page number inside the TLB and get the translation out before I can give the index to my cache and start looking into the cache. Now, this means that I need to sequentialize the access to the TLB with the access to the cache. And because L1 has to be extremely fast, I really don't want that. So what I'm going to do is that I'm going to constrain myself to have L1 caches that are always sufficiently small so that I can go and use the virtual page address. Is essentially the same reasoning that is in favor of us, right, for the attacks. We want to know from the virtual page already the index to put into the L1 cache so that I can do this immediately before I have a translation, and in parallel do the translation of the virtual page into physical page. This is very important for me for L1, and therefore I have by construction this index plus offset within the virtual memory offset by construction in every practical system, and I can exploit it. So attacking L1 caches is almost always no problem. Where it is a problem is in the other levels of caches, because there I do not have anymore this pressing urgence to read, because they are caches that I read only after I got a miss from the L1 cache, so they will take much longer. And by the time that I will arrive to L2, last level cache, and so on, I will already have done my translation. And so it will be no problem to have all the other bits from the translation. And also for those caches, it's essential to be much bigger or much bigger than L1. Okay, so all this tells us that if we have an L1, we are almost sure to get away with what we have seen before. And actually that explains why these attacks we had before worked, is because we were interested in accesses that were only where the access to L1 was enough to reveal the secret. Now, why are we interested in bigger caches and last level caches? For a number of reasons, but one of them, maybe the most important one, is that maybe we have attackers and victims in these modern systems that share some cache levels, but don't share at all other higher cache levels. So if I have the victim here, you see here a relatively old Intel architecture, but still in the last few years. If I have the victim here and the attacker here on different cores, the first shared cache that I have is the L3 cache, and it is certainly a cache that has many more index bits. There is another reason why it is interesting to address larger caches, which naturally are caches in the lower level of the hierarchy, closer to memory, and therefore like the last level cache. And this has to do with the resolution of the measurements of the information that I can obtain from these accesses. let's go back to one of these diagrams to get a sense of it. I already said before that within one cache line, we have no resolution. We have no resolution because essentially all these 512 bits of data, these 64 bytes, are all evicted and all brought in at the same time. So whichever I hit, whichever I use, whichever I discover something, it's confused among all the 64, right? There is no way to make a difference between them. There is another aspect that limits my resolution, which is through probing, I'm probing each of these sets and multiple ways one at a time. So I get information that is only proportional to the number of sets that I have. So if I have larger caches with a larger number of sets, I can learn more information or can differentiate more addresses of the victim and learn more precisely information about what is happening. Now, there is one property that is important to remember in how most of these multi-level caches in multi-core processors work, which is this inclusion property. This inclusion property says, and again, I suppose that you have seen this in previous courses, but this inclusion property says that whatever in for instance, in this example, in L1D cache, is certainly a subset of what is in L2, and what is in L2 is in turn certainly inside L3. And they have to be in the same state. There are a number of rules because this makes it possible to maintain coherence. It's not terribly important for us now here to understand why this inclusion property is enforced in these systems. What is important maybe to understand and to remember is that if the attacker goes and evicts something, or if the victim evicts something in L1D, this will be evicted also in L2, and it will be evicted also in L3. And this is something that we are going to use, or at least need to understand. Now, how do we handle this problem of large caches? One first way that we have to handle, maybe a brute force kind of solution that people have shown can be made to use, is that many modern processors have hardware support for large pages. Although most of our systems still operate with 4 kilobyte pages, and this since very many years, where sort of this has sort of emerged as the standard page size for almost every system. The TLBs in the hardware of most contemporary processors support very large pages, like 2 meg pages, or even 1 gigabyte or 2 gigabyte pages. The reason for that is that if you have applications that have an extremely large data footprint, with very small pages, you run into page misses or TLB misses all the time, right? Suppose that you are going through a huge data set, so you know that most of them will be misses because that's life. But while exploring this huge data set systematically, you keep passing these 4 kilobyte boundaries. And after a while, all these will become TLB misses. So in that case, you don't care too much of the cache, but or you hope that maybe the cache is in very for a very short temporal time is useful for something, but overall it will be practically useless. What you care is that on top of that, on top of a very bad cache performance, you don't have also an extremely frequent TLB misses and interventions of the OS and so on, which are always extremely painful because take maybe thousands of cycles. So if you have extremely large pages, this will happen much more seldom. Now you need to have administrator rights to set the large pages. You can typically tell to your OS or in the guest OS which size of pages you want to use. But if you are doing attacks in this kind of system, and if you are a guest operating system on the side for you, attacker, and the victim is using a different guest operating system, actually this works in your favor because both the operating systems will share the same L3 cache, but since you are the complete master of your operating system, you have the administrator right to set one of these large pages. And of course, the problem that we were discussing before is gone, and you are perfectly in control because now you have 30-bit offset, which is most likely certainly bigger than the index plus offset of any practical cache today, right? Because this is 1 gigabyte and nobody has 1 gigabyte of last level cache. Now, there is another way to do attacks in the last level cache, and is a modification, but a very cunning modification of the original prime and probe attack. So I remind you of what was the prime and probe with this simple image where there is a single set in the cache, the set that we are interested in maybe. And remember, the idea is that we prime it, we put our stuff in all the ways, this blue stuff. We run the victim that potentially will bring in the golden stuff somewhere, and we'll figure out if the victim has or has not evicted something from our data set by finding if there are missing, by probing the different ways and see if all our stuff is still there or some has gone away. Now, this hits the problem in the LLC that since the LLC, since the L1 is not shared, but only LLC is shared, the victim may have polluted the LLC, but we don't see anything in the L1 cache. And therefore, when we probe, instead of probing the LLC, we are actually probing the L1, and L1 is going to obscure the information that we are trying to read. Now, to some extent, maybe depending on the situations, actually inclusion may be your friend, right? If it turns out that what has been evicted by the LLC is one of the piece of data that are in L1, it would have been evicted. You would see not the piece of golden data here, maybe, but one of these data sets that are gone, which for you is the same thing. Now, I'm assuming, by the way, that the LLC has potentially more ways than your L1, which is usually a pretty realistic assumption because for a number of reasons is both what you want in your system and what you can reasonably afford to have in your system. So how do you do for not having the L1 intercept what happens in the LLC, which is what you are really interested in? And the cute idea is to do what is called a reprime. That is to go and evict yourself from L1 all your stuff. So you primed it first with the blue stuff, and to prime with blue stuff the LLC, you have also primed the L1 naturally with the blue stuff, and now you evict everything that you have in L1 in this set, and you put something else. Now you're going to tell me, but if I put something here, because there is inclusion, it must also be in the LLC. So how come here I have still all my blue stuff and none of this green stuff that is in the L1? Now, these are the tricks that one has to be careful with in caches and with this addressing, is that the number of sets in the LLC is usually much bigger, is what actually started the whole problem that we have with the LLC, is that there are many more sets because there are all these bits that are not used to index the L1. But now I can use it to my advantage, right? I can use these bits to put the green stuff. And since I differentiate the blue stuff from the green stuff through these bits, they will land in the LLC. They will be inside the LLC because, again, there is inclusion, and so it has to be there, but it will be in a different set. Okay, so I hope you see, right? The idea is that I can use for as blue sets whatever I need as an index and 0 in these few bits, in this case 5 bits. And then when I want to reprime, I use again whatever I need in the index, but I'm putting 1 in these 5 bits. And therefore it will land exactly in the 1 everything will land in a different set in the last level cache, but in the same set in the L1 cache, so that I will evict. And now, of course, when I go and I find misses from the original blue, so now I want to reload these, I will either have hits in the last level cache or misses that will require to go to DRAM. So I will have misses certainly from L1, okay, but I will measure hits or misses in the LLC, so between maybe 20 cycles or 100 and some cycles, depending whether it is a hit or miss. So I will see exactly what happens in the LLC. The machinery is a little bit complicated, but I hope you appreciate the high potentials that one has by manipulating appropriately all the different bits of the accesses that one is doing. Another question that I think it's time to ask is, what happens if we have an asynchronous attacker and victim? So far we have said whenever I want, I will trigger an encryption of something and I'll discover the secret key that is used in this encryption by my victim. So my victim somehow is triggered by me whenever I want to do whatever I want, which is maybe a very strong assumption. Maybe is okay in some cases, maybe in some cases is not okay. Maybe we have the attacker that is in one virtual machine and I have the victim that is in another virtual machine and is doing continuously some encryption with some key. And there is no way that I can synchronize myself. I can know exactly when is doing what operation. In fact, is just completely asynchronous. Maybe in the other virtual machine, there are other processes that are running that are doing something else completely different. So here is an attack that is an example of such an asynchronous situation between the attacker and the victim based on code access. So on observing which parts of the code the victim is executing at a given time. And this one in particular depends on a characteristic of typical virtual machines that implement something that is called page deduplication. essentially what happens is that if different virtual machines happen to load the same pages from disk and put them in memory, and the content of the two pages is exactly the same, the virtual machine, to be more efficient, to use better the physical memory that exists, the hypervisor will have different virtual pages in different operating system, in different processes, point to the same physical page and have a single physical page for all the users. Of course, there are a number of complications in the implementation of this, because if one of the virtual machines, or if the user of one of the virtual machines decides to write in one of these pages, of course, the duplication must be stopped. So essentially, it has to block the write, duplicate the page, have two copies physically, and let write one of the two. So there are a number of complications, but this is a very important optimization in virtual machines, because you can imagine when you have a data center that is, and all the virtual machines are running Apache, well, they have all the same code pages, all the same DLLs and so on that are loaded. So if we can load them all only once and keep them only once in memory, there is a huge advantage in terms of the usage, the quality of usage, of the efficiency of usage of memory. So this happens, this exists, is a feature that exists and is particularly useful, especially for code, which is exactly what we want to attack. So the idea here is to discover which parts of code are being accessed by the victim, so that we can discover some secret by understanding what is the internal state of the victim. What we see here is a modification of the prime and probe attack that we have seen before, but adapted to this situation where the victim and the attacker, although virtually addressing different pages, are actually addressing the same physical page. And what we want to see are which locations our victim has accessed. So we will flush the cache, which is the blue here. So this is time, horizontally is time. We will flush the cache, and periodically we will let for some time, we'll wait, we'll do nothing for some time, and then we load all the things that we are interested to see whether the victim has accessed. Now, if the victim has not accessed anything that we check, because we flush the cache, as soon as we try to reload this information, we'll have to load it from the first for the first time, and so there will be misses, and it will take some time. But if in between our victim has addressed, again with a different virtual address, but the same physical address, the same piece of code, has accessed this code, it will have a miss, because again it has been flushed, so it's the first time that is being accessed. But when it will come to us and we'll do reload, we will actually find them in the cache, and this will be the sign that the victim has accessed them, and then we'll flush again and we'll repeat. So we will sample every now and then, and this now and then depends on how much we wait. We will sample which of those points of interest that we reload in this red phase, which one of them have been accessed during the last wait period by the victim. So we basically have a trace where we sample and we see what has been accessed. Of course, we will have problems, right? It may happen that the victim accesses during our reloading, so it's masked, we don't see it very well. We may have measurements where our time is strange because it's in between a hit and a miss, because our miss is resolved by the fact that there was an ongoing miss on the side of the attacker. We will confuse one or multiple accesses from the victim. So there is a number of things that will not be too precise, and we can influence only partially by changing this wait time. But here is an example of what it may happen, and is again from the paper that first implemented this kind of attack, which I find is incredibly curious, interesting to see. This is the probe time for 3 locations corresponding at 3 parts of the code of the cryptographic primitive that is being used. And again, we are using this virtual page deduplication in the sense that we have loaded the same library. We know which library the victim is using, and we load the same library. By loading the same library, we know that the virtual machine will deduplicate the page and will make us address the same page. And we know some locations inside this page or pages that correspond to some specific cryptographic primitives that we are interested to observe whether the victim is executing or not. And now we have a number of points in time where we sample and we see what has been executed. And you remember that if we see a long time in our probe phase, it means that it has not been accessed by the victim, so it has not been executing. If it is very fast the time, it is a hit, so it has been executed. And so if we look at this time series here, we see the sequence of operations that our victim has done. And so if we zoom in, for instance, we see that it has executed 3 times the code that corresponds to the square primitive, and in the same time slot has also accessed the reduce 3 times, and so on and so forth. And we may know something, and we need to know something about this cryptographic algorithm that, for instance, says that if it has done square, reduce, multiply, and then reduce, there is something that I can learn about the secret. For instance, there was a set bit, a bit that was 1 in the key. And so by going through this trace, I can tell when there are ones and zeros in the key and eventually learn the complete key. So you see how, and I think it is interesting to look at these graphs, is you start from something that is extremely abstract, let's probe and so on and so forth, let's prime and probe. And then what you see is something extremely clear. You just have to play a little bit with the parameters. You have a lot of noise, right? You see here this modulo that took a particularly long time. What happens? Maybe a system call. Some of the things are partially unexplainable. There are missed slots because something happened and nothing worked for a few sets. But it doesn't quite matter, right? The point is that you see a lot of things with whatever noise there is in a pretty clear state. There have been a gazillion of papers that have been written since 2005 when the first successful cache attack was demonstrated. It's certainly not my point here to go and try to make any form of survey or taxonomy of all these of all these attacks, but I hope this gives you a sense of how powerful these attacks can be. And this is one class only of these attacks, and actually also one that is very hard already to fight. The huge amount of research has not gone only into trying to do better attacks, more efficient attacks, or more effective for specific use case and situations, but also for trying to find mitigations at all possible levels, doing processors that have caches that are resistant to attacks, or finding generic software solutions to the problem. Now, hardware solutions don't work very well. I think there have been a gazillion of them. None of them is in your Intel processor, AMD processor, ARM processor. None is truly effective and efficient. Essentially, all of them make your cache a worse cache, and therefore compromise in ways that are seen as non-tolerable the performance of your processor. Practically all these generic software solutions boil down to some form of cache coloring. And the idea of cache coloring depends from this graph, this image that we have at the bottom, which to which we are already familiar because we have seen a number of times today. The idea is again that the operating system that knows which virtual page, what is the mapping between virtual pages and physical pages. The operating system is the only one in control of some of the bits of the access. So there are these bits that have an influence on the cache sets being used, and are not controllable by the user. And so the idea is to give pages that have split basically memory as a function of the values of these 5 bits, and give to a user only pages with a particular combination of bits of these 5 bits. So essentially there will be 32 combinations in this case of different combinations of these 5 bits. So we call them 32 colors, and I'll give you only pages of a specific color to each of the processes. And the idea is that then each process can only access some sets of the cache. So it's essentially a partitioning of the cache that is done by the operating system. Of course, this is effective because since one process has only access to some of the sets and not the others, cannot do anything in cache attacks about the sets of the other. But of course, it reduces once more the efficiency of the caches, the effectiveness, their ability to essentially it reduces the size of the cache for each of the applications, and this is not necessarily a great idea in practice. What has been found as mitigations that are probably the only one that are implemented is application specific. So in a very specific piece of software that I think could be attacked through cache mechanism, I will write my code in very peculiar, very strange ways, in such a way that maybe I have a loss in performance, and maybe not, depending on what I'm doing, but I make myself less sensitive. One of the things is that maybe one of the dramatic one, there may be less dramatic changes, but for instance, if the S box can be attacked by looking at where I am accessing the array that contains the SBox. Well, it turns out that SBox can be implemented in different ways by looking at their mathematical function that the SBox implements, and so by doing computation instead of accesses to a lookup table. And now that is computation, maybe sensitive to other problems like timing attacks and so on, but from the perspective of the cache, maybe there is nothing that can be told. To end the lecture of today, I want to look at a couple of attacks that had a lot of attention in the last few years since they were published. And the reason is that they attack other parts of the microarchitecture that perhaps nobody thought of attacking before, or nobody thought that they will be so susceptible to leak. And these parts of the microarchitecture that are attacked, and we will see them in the next couple of examples, are fundamental parts of our microarchitectures that we all have in all our processors, are things that we have been developing in our first part of the CS470 course, and that suddenly become a major problem for security. So the first of these attacks is called meltdown, and is one of these catastrophic attacks that makes it possible to read the complete memory of a process. We'll discuss in a moment exactly what this means, but essentially it means that I can go and read everything, all the protected kernel data that are in my process. So it's not an attack of a victim of another program that is running. Is just that I am told that I can read only part of my memory that is open to me by the operating system, and suddenly I can read everything else too. So the applications of such an attack are left open for you to imagine, but clearly it seems very powerful. As I said, it's based on some relatively standard microarchitectural features, actually on the implementation of these features. So it happens that there are some processors that are resistant. They are resistant completely per chance. It's not because it's a better design or is a more clever design. It's just because they happen to be done that way. And what meltdown exploits is the erase condition. It will be more clear from the example, but is the erase condition between the fact that we make a memory access that maybe is not legitimate, but maybe we start making this access anyway, and the protection checks, that is discovering that maybe I was not allowed to do this memory access, but still I initiated. So whatever happened of the memory access may have left some traces somewhere. And again, the cache are these somewhere. Maybe the fact that I made a memory access that is not legitimate has already influenced the state of the cache before someone discovers that I should not have done this access. So the summary of the attack, and we will review again these 3 lines in detail in a minute, but is that we do a forbidden access at a location that I'm not allowed to access. I use speculatively this result. I force my processor to speculatively use this result to leave some side effects in the cache before the processor or the operating system, whichever, discovers that the access is forbidden and squashes everything from the system. So there is no architectural leak, right? Because eventually everything is squashed. But the key of the thinking is, if I can leave some microarchitectural trace, that one will not be deleted. and that will tell me something of the secret. To understand this attack, we need to understand some maybe peculiarity on how the operating systems typically handle the user space of the users. One could expect that in my user space there is exclusively what belongs to me, right? In my memory addressing, whatever I can address is exclusively what belongs to me, and there is nothing else. In fact, this is usually not true. What happens is that, of course, there is nothing else, there is nothing about the other processes, the user space of the other processes, because I have absolutely no reason to have mapped in my space their own pages. So process A has only green pages and process B has only blue pages. But there is one exception, is that the kernel has a number of pages that are interesting for everybody, like all the pages, all the some parts of the code for the page walking, some parts, some page tables, some basic page tables that are of interest every time that there is a TLB miss. And so these parts of the kernel are mapped into every process in some specific virtual addresses. Now, this has nothing to do with violations of confidentiality, because, of course, these pages are marked in the page table and therefore in the TLB as not readable by the user of which this process is. So the user, the green user, cannot read these pages, but they are mapped into its user space. And this is the source of the problem, right? The fact that we cannot access something, but it is mapped into our address space. So we can emit the correct address to go and read there. So let's go back to the description that we had, and let's try to build piece by piece some code that would create the problem. The first thing is to access something forbidden. So thanks to what I just said, I can go and read something that is secret and I could not read by simply making an access. Now, this access will not succeed, but I can express it, right? I can do a load to that address. So in C, this is what I will write, right? And wherever is whatever address I am interested to read, a pointer to whatever address I'm reading. Now, the second element that I want is to try to speculatively use the result, which is very easy, right? In a sense, I get this value. Well, I will not, because it will be blocked, but speculatively, maybe it comes. And once I have it, I can do something with it. And what I want to do is not anything. I want to do something very specific. I want to do something that leaves a side effect in the cache. So what does it mean? What I want to do is that I want to use this secret, this return value, to access memory. For instance, to access an array and to access different positions in memory depending on the value of the secret. Now, if I know which parts of the array have been accessed, I know what is the index. And if I multiply the index by a sufficiently large number, it will end up being in different sets. So by knowing which sets of the array has been accessed, I will know exactly what the secret was with resolution that is perfect. And this is exactly the code that we can use. Through this, there is something that is left in the cache. If I do an attack on the cache after doing this, I will figure out exactly the secret that was leaked. Why is this going to work? The idea is that the secret, which in C seems to be a different variable, but in reality is simply a register, a value, the result of a load, and this result of a load will be stored in a renamed register, and this renamed register will never be committed. I know it because this wherever is not something that I can read, and therefore it will raise an exception. But since it will go into a rename register, it will be used speculatively. And here is maybe a view of this that is more familiar to us if we go back to our first part of this CS470 course, where I have translated here in the top left the key parts of this speculation in assembly, in MIPS-like assembly. So I am loading from a wherever address into R3. I'm multiplying R3 by 4096. I'm adding some base address, which essentially is this array that I construct in my user space, and I go and read at this particular address that I've computed, and whatever I load, I put it in R4, and in fact, this is something that I don't even care. So this one is the load that is illegitimate, is the load that will raise an exception. This load is done inside this array that is an array that I allocated and that is completely legitimate. And what I will want to discover is through a cache attack to my own cache, to discover my own address, I want to discover which load word I have done, because the effect of this load word I'll never see because it will be squashed. So let's look at it in the reorder buffer. I hope you still remember this image that is consistent with most of my images in the first part. I have here the different instructions that start from whatever it is, 10 million C, which is this load word. And is the situation at a point where I have read the first load, the SLL, the add, and the second load. And we see by the tag that, by the absence of the tag, that the first load has been executed. In fact, I also figured out that is an exception. But since it has been executed, I got the value inside the processor already, is not in the architectural registers, but is here. The shift logic left has computed the index of the array that I want to address, and is here. And the add has added some whatever base address to this value, and the execution of the legitimate load has started. I don't know the result, but is executing. So sooner or later, and more sooner than later, the cache will be reloaded with this address. And this address depends on the secret. If I had primed the space of the array in such a way, but basically flushed the complete content of the cache so that nothing of the array is in cache, if after the exception is discovered, which will be discovered, for instance, in our examples, is usually when the head arrives here, I discover that there is an exception, so load has maybe already executed. We will not commit, we'll raise the exception, which means that we will jump at the address of the exception. Too bad, someone will discover that we did something naughty and will kill our process, nothing more severe than that. And all these operations that have been executed, including all the traces in here of my secrets, will be squashed. But there is trace in the cache by having one particular value that has been loaded. The value is irrelevant, but which value has been loaded tells me which was the value of the secret. So it is extremely powerful and very interesting, this combination of the problems of speculation that have a lot of microarchitectural state that is taken care of to make disappear and never percolate in the architectural state, so that isolation of process is honored, but cannot be prevented for leaving some other microarchitectural trace that is observable. So who's affected by this problem? And this is one of the severe things, is that almost anyone that does speculative execution is affected. It turns out that AMD is not affected. As I said before, it's completely per chances, because the organization of the core inside and of the microarchitecture is such that the check of the protection is done before letting the secret propagate in the architecture and create problems. But it's completely per chance. Tomorrow there will be a different mechanism that is somehow similar qualitatively to this one. Probably AMD will be a victim too. What can you do for this? But there is an obvious proper solution, which is change the design, essentially make everybody do deliberately what AMD does per chance. The other mitigation, the other only thing that you can do, and especially the only one that you can do for systems that have already legacy processors that are there and you cannot modify, but you want to secure, make them more secure, is to isolate the user space from the kernel space memory. Now, there is one way that you probably could do, which is to completely remove the kernel mapping of kernel pages in the user space, or at least map the absolute minimum to have a jump to kernel mode. But if you do it, it's extremely lossy in performance. So what people have decided to do is something a little bit in between, where you keep a little bit of the kernel space visible in user mode, and you need to go into kernel mode to see the rest of the kernel space. It's essentially a different way to manage the page tables and to accept their visibility in the TLB. Basically, they put the translation in the TLB or not. It seems to work. It has been implemented in Linux. It has been implemented in something probably very similar in Windows 10. It's not a totally complete solution, because there are still parts of the kernel space that are visible, but you may try to make sure not to put anything really important in there. And it has a performance penalty that there have been plenty of people trying to measure how much worse Linux is after the mitigation. And numbers are between 5 and 10% and up to 30%, which is relatively significant. Which sort of comes back to say there was a reason why the complete kernel space was mapped. It was felt completely safe before. Actually, the correction that has been applied in Linux was very fast because there was something that people were doing for different reasons. Basically, the same mitigation was there for different reasons, and suddenly it became much more important to use it, and it became part, I think is maybe even activated by default in Linux when you install it now. The last attack that we are going to see is Spectre. It's an attack that is probably much more catastrophic than the previous one, but maybe a little bit more difficult to make it work in practical situations. The reason why it is more catastrophic is that you cannot only read, you can break memory protection completely, but now not only to read any part of the memory that is mapped in your address space, but any part of memory. You can go and read whatever you want. We'll see why it is a little bit more difficult potentially to implement. For instance, I believe that nobody has observed yet, or at least has said to have observed a Spectre attack in a realistic situation done. So they are only demonstration of the fact that this attack could work. And it addresses another shared resource that we are not necessarily thinking of. That's why also I think this attack has sort of shocked people, because there are so many things that are shared, but we don't even think of them. And one are the branch predictors. So we may have the same branch predictors because it's convenient to have only one set of branch predictors for all the users of a core. If you remember, there was this in the lecture on simultaneous multi-threading. I think there was a slide that was asking the question, because the authors of the simultaneous multi-threading asked the questions of, do we need to have the same branch predictors, or do we need to have different branch predictors for each of the virtual threads that are going to run? And one of the practical conclusions was that empirically one finds that you can leave the same branch predictor for everyone, and in terms of performance, the fact that there will be potentially some aliasing between my branches and your branches are not too bad. So we were happy that we could share the branch predictors, and now the fact that we share them create a huge amount of problems. What we exploit here is the side effect of mispredicted speculative execution. Like before, we were speculatively executing a load and some instructions that depended on this load, and we wanted to have some effect, microarchitectural effect that we could measure. Here is essentially the same thing, but the speculation depends not by a not yet seen exception, but by a mispredicted branch. So the idea here is that we get the victim to execute some leaky code, some code that will reveal some secrets, and to do this by wrongly speculating. We force the victim to wrongly speculate, and we want this leaky code to have some non-architectural side effects that we can observe. Now, the difficulty is that here, I didn't make you notice this before, but before we were talking of what we do. So it was completely our code that we were executing, and we were doing a sequence of operations that was suited as well for the attack. Now, what we need to do is to find a piece of code of the victim that has essentially this behavior. Now, the behavior that we want is that we want to have something in that the victim can do that can read a value anywhere in memory. So this is not particularly difficult, right? Because any access to an array, for instance, or similar access with an offset, if I change the offset, I can access anything that I want. So speaking C, by putting in this index whatever value, I can read any part of the memory. Now, the point is that this is the victim code, right? And that's why the victim can read any part of the memory that belongs to the victim. It can because is the victim, so can read whatever it wants. But of course, the victim programs well. And if the victim programs well, it will make sure that this particular instruction is executed only if it is legitimate to do that. For instance, there will be this test that says don't go into reading array 1 unless the index is small enough. But we can try to get the processor to mispredict this branch so that the access to array 1 will be done anyway. And now what we want to do is exactly the same thing that we were doing before, which is to find that this leaky access, this access that reveals the data and that is accessed speculative, that is, will be squashed, will never report any result architecturally, leaves an a microarchitectural trace, which is exactly the same idea as before. If I make a memory access indexed by that, I will leave a trace that a cache attack may do, right? So it will remain in the cache. So if I can force the victim to speculate, and if I see that there is in the code of the victim something that has essentially this structure, then I can do it and I can make a prime and probe cache attack to learn what is the secret. So I say this attack has not been observed, or at least not reported to be observed in real life. This is not necessarily because, for instance, this piece of code is difficult to find. Again, this code must exist for the victim, and we must be able to trigger it when we want. So there are a number of conditions that are difficult, but if you think about the type of code that we have here, it's not necessarily so difficult to find, right? Because we need to have some indirect access to memory, which we do all the time, where the first access is done through a variable that is correctly protected. So it's not that difficult, right? Essentially, what we are saying is an indirect address correctly protected, which is something that is not so difficult to find in code. Again, maybe one difficulty is that we need to be able to force the execution whenever we want, and we need to bring an X, this value, the index that we want, so we must force that it comes from the code previous, but for instance, it may be from, I don't know, the input buffer or something like this. Exactly for that reason, there is a test that says, okay, but if you give me some crap as the input, I will not do anything with it. So it's debatable how practical this attack is, but the point is that it's extremely dangerous, and practically every processor that we know of and that has a speculative execution is a victim. In fact, for instance, AMD, that was not was resistant naturally to meltdown, is not resistant to Spectre. So what can it be done? Not much, right? That's the problem, right? In hardware, what we can do hardware without speculative execution or disable it. It's crazy, right? I mean, it nullifies everything that we have said about the progress of processors and computer engineering. We may be able to separate the branch predictors per process and thread. Maybe easier per thread, per process is really heavy, right? Because I have hundreds of processors. If I have to have hundreds of branch predictors, it's not gonna work. I could flush them, but then again, I will get other type of performance issues. General software approaches, there are almost none, except saying this is a sharing at the level of a core, so let's put only one application per core, right? Yes, maybe, but it breaks a lot of things that we do. Of course, in cases of data centers, banks, and so on, this is probably what people would implement. Application-specific software approaches, yes, there could be some things that could be possible. For instance, have some sort of disabilitation of speculative execution ad hoc, where there are secrets to be learned, so that basically only some parts of software are going to be slower, but at least they are going to be secure. An idea to do this is simply adding some serialization instructions between branches and loads. I invite you to think about what this means, right? Because remember, we have been looking, we looked at it particularly carefully at the time of Itanium, of the statically scheduled processors, and there was this advanced, I think it was the advanced or the I never remember which one, which is which, but one of the two advanced or speculative loads that existed exactly for this purpose, right? Advance a load over a branch. And now we are saying that thing that Itanium had to implement, because otherwise performance would have been a catastrophe and incomparable with dynamically scheduled processors. Now we want to suppress. Now, again, if you suppress it specifically when you really have a problem of a secret, maybe is acceptable. But you see that we are sort of trying to go against everything else that we have done. In some specific context, like for instance in the JavaScript engines that exist in browsers, for instance, because you have a very much more constrained execution environment, it may be impossible to have this thing. If you look at what the authors of the Meltdown and Spectre attack, which are the same people, who are the same people. There was a quote that I think is interesting. They actually say this about why they call it Spectre, but the point is, as Spectre is not very easy to fix, it will haunt us for quite some time, which is quite probably true. So we have seen a few attacks. The purpose, again, is not to go through all of them, but to have a sense of what are the primitives that exist and how these primitives tend to go exactly against all the things that we try to do to guarantee performance or to extract more performance from our processors and programs. Real attacks are typically a composition of these primitives in the spirit of maybe Matryoshka dolls. You see it a little bit of this in this last Meltdown and Spectre, where you put together cache attacks with attack to predictors or to this execution exception weakness. real attacks are made of a succession of partial attacks to learn something, and then use this to learn something else, and use something to learn something else. One way to look at it is to say that it is, I want to say, really a huge mess, because we are going in one direction for some good reasons with the computer architecture to try to be efficient and effective, and all these things will come back to us without very clean solutions. So we'll speak of some solutions at the hardware and architectural level next week, but maybe the results will not be so comfortable as we would like them to be. Thank you very much. There is a bunch of references on the last slide. Some of these references are also on the web for you to read them if you are interested. Have a great week, and let's continue next week.